So, we've now seen some nice examples of using guess and check methods to find answers to things. But we want to take a slight detour. We'd like to use guess and check, but not just for integer values, not just finding cube roots of integers. We might like to try and find them for other values. But to do that, we have to think about using floating point numbers, or floats. And to do that, we also then need to take a little bit of a detour to understand how floats are represented inside of the computer. So bear with me for just a little bit. We're going to talk about floating point representations and then bring that back to see how we can still use those ideas to find approximation algorithms to get solutions using guess and check methods. So floats approximate real numbers, but how do they actually do this? And let's think for a second though, what is a decimal number, the kind of number we normally deal with? Well, 302 is really 3 times 10 squared plus 0 times 10 to the first power plus 2 times 10 to the 0th power, which of course is just 1. So it's 3 times 100 plus 0 times 10 plus 2 times 1. That's because we're using base 10. Handy because we got 10 fingers, 10 toes is an easy way to do counting. Computers, not having fingers or toes, do things a little differently. They represent things in terms of binary numbers, or powers of 2. Basically because in electronics it's easy to have a switch either be on or off, have a 0 or a 1. So a binary number will be a sequence of 1s and 0s that has the same form. So the binary number 10011 is the same as 1 times 2 to the 4th power plus 0 times 2 cubed plus 0 times 2 squared plus 1 times 2 to the 1 plus 1 times 2 to the 0, which of course is 1. So if we wanted to convert it to decimal, that's basically 16 plus 2 plus 1 is equal to 19. So decimals, base 10, binary numbers, base 2. Internally, the computer represents numbers in binary form. So one of the things we'd like to figure out is, so how does it actually get to that kind of a stage? So let's look at that. What does it mean to think about converting a decimal that we type in into a binary form? How does the computer convert it into a form it can use, and then how are we going to think about that? Well, let's take an example. Suppose we give the computer some number, we'll call it x. And it turns out x is actually 10011 in binary, but we don't know that. We want to figure that out. Well, knowing that it has some form like that, what could we do? The first thing we can do is if we take the remainder of x with respect to 2. Okay, what does that say? Well, it says if we're going to divide each of these elements by 2, since x is this sum, we can divide that by 2 evenly, we can divide that by 2 evenly, that by 2 evenly, that by 2 evenly, but this one we cannot. So when we do that, the remainder that's left is whatever that bit is. And that gives us the last binary bit, which is a 1. That's cool. It says taking the remainder of x with respect to 2 gives us the lowest order bit. If we then divide x by 2, what we really do is we just shift the bits left. To see that if we divide x by 2, that's going to change that to a 3, that to a 2, that to a 1, that to a 0. This goes away, because remember we lose it. And what we've done, is get exactly that form. We've shifted all the bits left by 1. And we can now do the same thing. If we take this new value and get the remainder of that with respect to 2, it's going to give me that, which gives me a second 1. And then shifting left will reduce that to 2, that to 1, that to 0. And I'll keep going. And that will allow me to successively peel off each of the bits in order. So we can convert any decimal number into a binary form. Okay? Here's a little piece of code to do it. Let's just walk through it very quickly. This part up here, I'm just going to let you look at it, but it's pretty straightforward. It's basically saying if the number I'm trying to convert is negative, I'm going to take the absolute value, but I'll keep track of that so I can put the negative sign back out in front when I'm done. And then what does this piece in here do? Well, it basically walks through what I just said. It says I'm going to set result initially to be an empty string. I'm going to gather up the bits. And then, if the number is 0, I just return 0. Otherwise, there's one of those little iterative loops. It essentially says, let me strip off the bottom order bit, put it onto the result. There's a concatenation of the string, puts it on to the left of whatever I've already gone. Change number by dividing by 2, which shifts the bits left, and keep going. So this is getting me the next bit. This is just shifting left. And I do that, okay, until I get a number that's less than equal to the 2. And when I do, I'm done. Result holds the thing I want. And all I need to do is just put a negative sign out in front if, in fact, what I started with was something negative. So this is just doing a conversion back. Cool. Let's take a check at this, see what it does. So here in idle, I've got an example of that. I've set number up to be 302. And let's look at what happens if I do that conversion. So I type it in. Nothing showed up. That's right, because I didn't ask it to print anything out. But I know that result now holds the value I want. And it says, as a string, there's 302 in decimal converted into a binary form. I could change it to something else. Make it 256. And do the same thing, save it away. And again, I need to see where the result is. I can do that. Oops, sorry, over here. Go back down to where I was. And here's result. Oh, and since I know 256 is a power of 2, that form looks roughly right. So what are we doing? So given a decimal number, we can convert it into binary form. And that's literally what the machine will do inside. Now, let's think about what this says. First of all, I want to be able to get good approximations to things. So what about fractions? How do I deal with a fraction? Well, let's think about a number like 3/8. In binary would be 0.375, which would be 3 times 10 to the minus 1, or 1/10, plus 2 times 100th, plus 5 times 1,000. So it has the same form. Now, how could we figure out how to convert this into binary? Well, suppose we could find a power of 2 big enough so that when we multiplied it by this fraction, it turned it into a whole number. If we could do that, then we could take the whole number, convert it into binary using the method we just had, and then when we're done, divide by the same power of 2, which is just going to shift to the right. So, for example, 0.375, we kind of know this. If we multiply it by 8, it gives me 3. That's in decimal form. I could convert 3 to binary form, which we know is just 0, 1, 1. And now that I've got that, I could just divide by 8, which is equivalent to shifting the binary point, if you like, 3 slots over to get 0.011. Cool. Let's do that. Here's my code. And it's really got almost exactly the same form. It's a little bit more than we had before, but let's just look at it. I've got something up here that's just going to input an x, so I'm not having to type new values in. And here's a little iterative loop that simply looks for the power of 2 that converts it into a whole number. So it's just going to loop over p, looking for a value of p such that 2 to the pth power times x is a whole number. Its remainder with respect to 1 is equal to 0. Cool little check. I'll just do that. All right. Once I can do that, then I'll take x and I'll multiply it by 2 to the p. I've converted it now into a whole number. And there, I just did what I did before. Simply run through that test to see how do I convert it back into a binary form. And once I'm done, then the last piece is I need to make sure I put enough zeros out in front by looking at how many values are there between the size of p and the length of the result. And then, having done that, I just need to find the right place to put the decimal point. And there's a funky little piece of code that is basically finding the spot in between p where we want to do it. We'll let you look at the details of it, but that's basically what this code does. Finds the power of p to make it a whole number, does the conversion, and then converts it back. Okay, so let's see what we got here. I'll go over to my idle, and I've got a piece of code that captures that. Right? So there's the piece of code right there. And let's run it to see what happens. So I'm going to run that piece of code. It says give me a decimal number, in this case between 0 and 1, because that's where I'm going to deal with it. Well, let's try 0.375. Runs through 3 steps to get the remainders, and it converts it into that binary form which we saw before, 0.011. Sounds cool. Let's try it again. Let's re-enter this, and let's, I don't know, something simple, 0.1. Oh, it's working away here, and it's working away really hard trying to find something. And it says, my goodness, the binary representation of the decimal 0.1 is, look at that, 0.00011, 0011, 0011, 001. Well, you get the idea. It's really boring and repetitive. So what happened here? That's a little different. We didn't get some nice, crisp, clean form. And in fact, that's going to be an important factor when we think about binary numbers and decimal numbers, and especially fractions. So what's one of the implications? If there is no integer p such that x times 2 to the pth power is a whole number, then the internal representation is always going to be an approximation. And in fact, what happened here was that the Python system eventually stopped trying to expand it out any further and simply gave us a representation out to some arbitrary number of bits that are set by the internals of the Python system. So if it's not something that can be turned into a whole number by a power of p, it's always going to be an approximation. This has an important implication. It says, well, I want to test two floats to see if they're the same. I shouldn't use something like this, because it might not be true, because the approximations may be slightly different. I'm always better basically saying, is the absolute difference between them smaller than some arbitrary amount? And we're going to use that a lot. This is a standard place where people get into trouble by trying to test equality of two floats and then being surprised when, in fact, the code doesn't do what they'd like. One of the things you could ask is, so why does print of 0.1 give us back 0.1 if, in fact, 0.1 is represented as this long, funky kind of thing? And the answer is because the designers of Python decided to set it up this way, that it automatically rounds to some number of bits in order to give something that's much crisper. But in fact, 0.1 is not represented as 0.1 inside of the machine. That's going to be important now as we think about taking this idea of iterative algorithms, especially guess and check algorithms, but dealing with floating point numbers. And we're going to do that in the next segment.